welcome to the course on material selection for mechanical design. Now, I am teaching you currently the attributions of material through different types of case studies. Okay? And today it is the part 3 of these attribution of material studies that we will be taking up. So, this is the fourth lecture on this topic. Now, just a bit of recapitulation. What we have talked in the beginning of this material attributes, that a material has many attributes. Okay? These attributes are nothing but the uniqueness of the material. Okay? Like for example, we have different types of uniqueness as human beings, and you consider any other species, they also would have different types of uniqueness. Similarly, materials also will have different types of uniqueness. Uniqueness, let us say from the mechanical property point of view, then there will be uniqueness from non-mechanical properties point of view, and then many other attributes, for example, the cost, for example, the performance of the system, all these things comes up. So, now the material attributes, that means, are a long list of all these things. Some are mechanical, some are non-mechanical. Now, for any product design, there is always a profile that is involved. Okay? So, that profile essentially tells us that out of many possibilities, which attributes are most significant and what should be the sort of specifications on them, like what should be the density. Low density means what exactly would be the density range that is approved. Then what should be the strength, whether it is a high strength, low strength, and all these things. Now, when we start to design, we start to design with all the materials. That means we keep our minds open. Of course, we will not take those materials which are prohibitively expensive, for example, gems and all these things, but with all the practical feasible materials, we always start with all of them. And now what we do is that we apply the property limits. That property limits is exactly what I told you, that what is the density range. Okay? I can allow the density, let us say the rho, if I call it, then the rho should be less than something. I just say it here, that 5000 kg per meter cube. So, that is my property limit. Okay? And suppose I say modulus of elasticity. Modulus of elasticity should be greater than 100 GPa. So, that becomes my property limit. So, this property limits, when you apply, immediately what happens is that from all materials you will come down to only a few groups of materials. Then you have to further use the performance index or the material index to further reduce the number, because material index will actually tell us that not just one property, but how two or more material properties are going to act together in terms of taking a decision. That is what is important. Okay? For example, you have seen earlier that in tension dominated design, from the stiffness point of view, E by rho became a sort of a material index, right. So, that means it is neither E nor rho, but it is E and rho combination you have to consider together, and that way the index defines that whether the material is having a value of the material index which is permissible or not. So, that is the way we take our decision on the selection of materials. So, what I will do today is that I have already talked about what are the cases that I have talked about. Let us say I have talked about tension, okay, pure tension, that is one thing. I have talked about pure compression, and then I have talked about bending. So, in order to introduce you to the subject, though later on we will consider many other cases, but I will consider now the case of what we call torsion, and I will take the case of shear. torsion and shear are basically like a twin, they are together. Wherever there is torsion, there is shear there. Okay. So, we can interpret them each in terms of the other. So, we will see that how corresponding to torsion and shear we can actually find out similar material property index. So, that will be the first part of all that we were trying to do. So, this will be with respect to material index. And in the second part of the talk, I will touch something which is also important. So, I will start to introduce that concept to you now, and that is known as Ashby triangle. So, what is this Ashby triangle which goes beyond the material index? That also we would like to cover up in today's lecture. So, let us go through the case for torsion and shear. Now, how I am going to isolate the material index? Well, the performance of a system, I told you earlier, that will be given in terms of function, in terms of geometry, and in terms of the material. Okay. So, you have a functional requirement part, geometric part, and the material part. And in most of the cases, generally the variable separation exists. So, you can separate each one of them. Where it does not exist? Well, if there is a microstructure present, then this does not exist. Okay? Then this become actually integrated, particularly the material requirement and the geometry requirement, these G and M, they get integrated together. So, in that case you cannot really write these three to be separate. Okay? Otherwise, in most of the cases they are separate, and hence from that separation we will only extract the material index. That is the policy that we are going to adopt for this case of torsion and shear. So, let us start with the material selection for torsion dominated design. Okay? Now, in a torsion dominated design, the primary load carrying mechanism is always subjected to torsion or twist. Okay? So, there are two different types of possibilities there, of course. Okay? One case is that when one side is like statically fixed, okay, or supported. So, one case is something like this, okay, and you are applying the torsion. And these are the cases which are cases related to, let us say, more civil engineering type of applications. Some cases in aerospace also comes in this category. For example, the aircraft wing. Okay. So, that would be also behaving like a cantilever beam, and this is subjected to sometimes not just bending, but also torsion. Okay. So, this is one group, and the other group is interesting, and that is this type of a problem, that is for transmission shafts. Okay. The reason why the first group is different from the second group is that for a transmission shaft which is generally more rigid, okay, its main job, primary job is to transfer the torque from one position to the other position through the gears, etc. Okay. So, this works like a torque transmitter, right. So, lot of things comes here, because the governing equation in this case will have the dynamics also involved in it. Whereas, the second case that I have shown you here, this is a typical of a aircraft wing. This is an aircraft wing, and here, for example, this is the vertical wedge part of the aircraft wing, and as the aircraft is actually moving, what will happen is that its edges, due to vortex, etc., is going to get a twist. Okay. So, this is going to have a twist, and this kind of twist is it is not transmitting the torque, but that entire structure is designed in such a way that it has to resist this twisting. Because what happens if the aircraft wing itself gets badly twisted, then the aerodynamic interactions are going to suffer. So, this is the objective in such a case, that you have to resist the twist. There is another case also. You must have seen lot of bridges or things like that, the factory sheds, where you are going to get this type of things like a gusset plate connecting the frames. Okay. So, this is a frame, and then the connections is happening because of these kinds of rivets, okay, rivets, bolts, etc. So, you will be having rivets, you will be having bolts. So, in both these cases, this system is going to get again a sort of a twist, okay, for tightening the system. So, all these cases we have to see that how we can figure out what will be the suitable material property index that comes into picture. Let us look into it one by one. Okay. So, first is that let us take a case of a solid circular drive shaft for power transmission. Okay. So, we have a solid circular drive shaft, that means if I take it up like this, which has maybe some kind of a gear system here, okay, and the shaft is getting sort of rotating in a certain direction. So, this is the torque and this is the omega, right, and this is the shaft and this is the rotor. Okay. This shaft is of course not in the free state, but there will be some bearing to take care of the sort of supporting forces to vertically sustain it, but these are just bearings, so that it just takes the vertical load, it does not restrict the movement of the shaft. Okay. If it restricts, then it will become a structure. Okay. Now, this shaft, suppose if I cut it here, and then in this case what we are assuming is that this shaft is having a circular cross section, solid circular shaft. Okay. So, that is the sort of the cross section A. Now, for this what we have to do is that we have to minimize the mass of this shaft while transmitting a specific given torque. That is the idea. Okay. Why do you want to minimize the mass? Well, we want to minimize the mass for two reasons generally. One is that if the mass is more, we generally find that this entire system becomes more expensive. Okay. Secondly, which is more important, is that if the mass is more in this particular case, then the inertia effect will be more, and hence you will need more torque to drive the shaft. Okay. So, the energy that you are spending to drive the torque may increase because of the shaft itself, but you really want the shaft to transmit the torque. Okay. So, you do not want to per se keep the kinetic energy inside the shaft, but to transmit it suitably through the set of gear sets and transmit it to where it is required. Let us say in the case of a automobile, it is required on the wheels itself. So, that is how the minimization of mass becomes an important point for this type of a design. So, our function is that you have to transmit the torque T, and our objective is minimize the mass m of the shaft. So, that means the density and the area and the length. So, the shaft has some length L and some area here, which I have kept it as A. So, let me just keep the cross section as something else, A prime. Okay. So, the cross section area is A. So, this is what we want to minimize. What are the constraints for us? Of course, the first important constraint is length, okay, because the length is coming from some other point of view, like you are attaching this shaft for transmission of power let us say from the engine to the gearbox or from the gearbox to the wheel, those were defined by other requirement of the car. So, this we cannot touch. Then the torque of course is fixed, of course it is fixed, because the torque is ultimately required to rotate the wheels. Maximum twist may also be fixed. Okay? That means, while transmitting, the shaft itself should not be so soft that the shaft itself starts to absorb the torsion in terms of twisting itself. Okay? That is an important thing, because for a structure that is what happens, but for a shaft that is undesirable. So, there is a maximum theta that will be allowed for such a system. Now, if that is given, then we have to definitely calculate what will be the angle of twist corresponding to a theta. Okay. So, if I consider the torque the shaft to be elastically deformable, then we know from strength of materials that theta is TL over Gj, okay, where G is the shear modulus. So, this is where you see the shear is now coming into picture. Also, for a solid shaft, J is pi d to the power 4 over 32. So, that is the J that we already know. Okay. So, now I can put all these things together. So, let us go to the next slide and see that how we can use this information in terms of the material property index selection. Well, one thing we have to keep here in mind, that we have to have a free variable. Okay. Now, that free variable can be the area itself, but more realistic in the case of a shaft is the diameter of the shaft. Okay. Whether it is going to have a diameter d1 or d2, we are free to sort of vary that diameter, as long as it is going to sustain that torque and that twist is within that limit. Okay. And also as long as it remains as a solid shaft. You see, I have not considered the hollow shaft or shaft of some other geometry, which I will talk about it later. So, now diameter is chosen as the free variable, as I told you, right. So, you know already theta is TL by Gj. You also know that J is known to us, right. So, we know that the J is what, pi d to the power 4 by 32. So, you can see it here, that from this equation, if I just write it here just for your clarification, that it is TL over Gj, which is pi d to the power 4, and then the 32 comes in the top, right. So, now if you look at it, that I can interchange, because this is the free variable and theta is given to us, because maximum twist is given to us, right. So, now I can interchange it and I can then write that d to the power 4 equals to 32 TL by pi g, and then that theta max or whatever that is given to us. Okay. So, that is how we have obtained this particular expression. Okay. If I know d to the power 4, I of course know what is d square, which is the square root of it. So, now I know d square. So, that means in the area which is A, I can substitute, that is pi d square by 4 L. So, I can substitute that expression of d square here, and if I do it, then what happens? Let us just try to do it in the broad hand here. Okay. So, we have some space here to do it. M equals to, now you have pi rho by 4, and then you have d square, that d square we have already talked about. So, it will be square root of little longish expression 32 TL, okay, divided by you have pi g theta max. I am just writing it as theta max, so that you know that this theta is not any arbitrary theta. Theta is not a free variable in our case. Okay. So, that and then times that length L. Okay. So, if I write the mass like this, then I can actually separate the variables now. You see, luckily here also you would see that the variable separation is going to exist. Okay. So, let us keep all the numerical constants in one part. So, that means root pi takes care of this pi and this pi. Then you are going to have 16, so 4 comes out, so root pi, and then there is a 2 there. So, we can actually write it down as root 2 pi. So, let us just erase it and write it as root 2 pi. That is done. So, this numerical part is taken care of. Now, you have L to the power 1 and half. Okay. So, 1.5 that comes out. So, that also goes out and divided by square root of theta m. So, all the geometric, the part that goes out of the system. So, what is remaining? Let us look into it. Okay. So, then there is a torque there. So, torque is the functional part, square root of the torque. So, that also goes out, and then what is remaining for us? What is remaining for us is the material property, rho by root g. Okay. So, this is the functional part, this is the geometric part, and this is the material property index. Okay. If you just go back 2 slides, I am just going back to just show you that that was the thing that we have done earlier. You see that F, G and M. So, that is what it is here, that this F, G and M. So, our M here is going to come out to be rho over root j as the material property index. Let us call it as Mi or something, okay, so that you do not confuse it with the mass of the system. So, now it is important. You have to minimize this mass m, right. So, if you have to minimize this mass m, that means you have to minimize rho over root g, correct. So, what we will do is that we will take the reciprocal of this. So, our material property index, which is capital M is defined as square root of g over rho. Okay. So, if I maximize this, then this part will be minimized and automatically our mass minimization will take place. So, I have to basically now choose that what combination of shear stiffness and the density is going to give us the maximum value of M, and that is the material that we are going to choose in the case where stiffness becomes dominating factor. So, now I have taken a lot of material here. Let us say I have taken carbon fiber reinforced plastic with 30 as the GPa. Okay. So, you must be knowing that you can always figure out G as E by 2 into 1 plus nu, right. So, where nu is the Poisson's ratio, Okay. So, you apply that Poisson's ratio and then you should be able to find out the shear modulus. So, the G you can get it like that, the 30 GPa, density is 1600, and then if you apply this for the square root of G over our material property index or square root of G over rho. Now, you can see that G is in gigapascal. So, hence we have kept one additional multiplication factor, which is 10 to the power 6. Okay. Then the M value, if without that 10 to the power 6, if we do, it will come out as 3.42, and this is for CFRP. Okay. CFRP stands for carbon fiber, one of the best for the this type of application categories. Okay. Carbon fiber reinforced plastic. Right. Now, another material that is used, can be used, okay, may not be for shaft in fact, that is magnesium alloy. The reason being, magnesium has a very low density, okay, similar to carbon fiber, it has a density of 1800. So, and the shear modulus is not so high, it is about 17. So, if you evaluate it, you will get, because of the low density, it will come out to be 2.29. The next possibility is aluminum alloy, so which has 26 gigapascal of shear modulus, higher than magnesium alloy, but the density is also high. So, the ultimately the square root of g by rho reduces this m to 1.89. Interestingly, wood is also a possibility, although it has 1 gigapascal of shear modulus, but it has very low density, 600. So, it will come out to be 1.67. Titanium alloy will come out to be with 4500, this will come out to be 1.47. Steel will come out to be with 807850, it will come out to be 1.14. And just I thought of keeping some ceramics also, just for your curiosity, that if I take a chalk like material, then it is 3 GPa, and 2500 it will come out to be very low, 0.69. Okay. Natural rubber, if I consider, that will be very low shear modulus. So, this will be the lowest. In fact, now if I look into the whole group, you would see that we have already ranked it based on the highest to lowest this material property index. Okay. Now, from here some of the things we are going to cut. Okay. For shaft, for very ancient days, we indeed used to use hardwood. Okay. If you look at the chariots, for example, okay, before the iron is discovered, wood used to take place, and it was not a bad choice. You see, with 1.67 it is better than steel. So, of course, it will be better than simple iron, but of course, what is the problem with wood is that it is not going to have durability. It is sort of susceptible to moisture, for example. That is the greatest problem for any natural material, that it absorbs moisture, then its property, it gets rotten very fast. Okay. So, the durability is of concern. Okay. Then there are of course other things that comes up, for example, the inflammability and that all other aspects of it, the wear and tear, etc. So, from all this point of view, hardwood you can cut. Okay. Chalk also you can cut. Interestingly, I will not cut the natural rubber, because even if it is very low, it serves a very interesting purpose, that is, it can be used as a flexible coupling. Okay. And that is why there are many different couplers. For example, there is a coupler called a jaw coupler, which is invariably having rubber blocks in it. So, what it does is that if you are connecting two shafts, so I have only shown you one shaft, but suppose you are connecting two shafts together, okay, and that is transferring the motion, then you will need a material which can get twisted, and the advantage there is that if there is a variation of torque all of a sudden, then there can be a possibility, because of torque difference, there can be a possibility of a vibration, and this fellow actually absorbs this kind of a vibration, and hence the twisting actually works in favor of us. So, I will keep natural rubber, though it is not used as a candidate material for such a case. I will also not keep magnesium alloy, again from that same reason, that for the shaft, magnesium alloy has lot of this wear and tear problem. So, it is not good for a shaft type of a system. So, we would actually then have practically CFRP as a possibility with us, aluminum alloy as a possibility, titanium as a possibility, steel as a possibility. Okay. So, these are the 4 practical possibilities with us, and out of that, even though the steel is the lowest, but you will see later on that the steel can actually regain its sort of position because of another possibility through the Ashby triangle. However, another point you have to keep in mind, that out of all of them, steel is one of the cheapest. The next is aluminum alloy. So, hence titanium alloy is more expensive, CFRP is the most expensive. So, even if CFRP is a good solution as a shaft, it will be hardly used unless it is a luxury car of the level of, let us say, BMW. Okay. So, for this type of situations they would be using CFRP as for that kind of a coupler. Okay. Okay. So, now, this is what I was telling you, that for torsional applications the jaw coupling with the rubber elastomer, that is a distinct possibility that happens. Magnesium alloy is not used, I told you, for torque transmission, but it is true that it has a good shear resistance, and hence it is used for car steering, you see, which is not subjected to a dynamic by sort of a condition. It is, you only occasionally rotate it. Okay, it is not a shaft which is continuously getting rotated. So, this, its endurance strength is not important, the fatigue is not important. For such a case, magnesium alloy based car steering is one case application where it is pretty common. And I told you that for shaft, for the most expensive side, there is this type of shaft which is called prop shaft. It is generally known as prop shaft. So, prop shaft of BMW is actually made of carbon fiber reinforced plastic. So, whatever material property index we have just now checked, they indeed have some application values, because people indeed follow it. So, that is most reassuring for us. Now, I told you that this twist or theta max is not the only consideration, cannot be for a shaft design. The another important consideration has to be the shear strength. Okay. So, in this case, the transmission of torque is T as usual, the same torque, minimize the mass m. So, it is mass is rho L, and for the solid shaft area is pi d square by 4, and our constraint is that the maximum shear has to be less than or equals to tau y. Okay. So, there may be some factor of safety there. So, what is the shear then for a given torque? That is TR over J, that we know from our strength of materials knowledge. So, TR over J, and we already know the J as pi d to the power 4 by 32, right. So, I already know that what is going to be the tau with respect to these R as d by 2 and J as a function. So, both of them are function of d. So, if you incorporate all of them together, then you get the expression of tau y. Okay. Now, the tau is tau y, and that is T d by 2 pi d to the power 4 over 32, which can be simplified as tau y as 16 T over pi d cube. Okay. So, now you can of course change the side, and tau y is something that is a material property. Diameter is a free variable, we already said. So, you can write that d cube as 16 T over pi tau y. Okay. So, that is what we have written here, which means d will be 1/3 of it, right. So, d will be the whole thing over 1/3. Okay. So, that is what is our diameter d, and then let us use this expression in the expression of the mass. That is what we are going to do in the next slide. So, we know already that the area is pi d square by 4, and hence that this square part we can substitute from our earlier expression of d. Okay. So, d square will be the same, and this will become 2/3, right. So, that is what is happening here, that the same expression, but with 2/3, that will come into picture. So, you get this entire expression here, okay, of the mass m. Again, you use the same strategy of separating the things out. Okay. So, if you separate the things out, you see what are the material properties that will be coming up here, right. So, have to see that it is rho, that is one material property, and tau y to the power minus 2/3, that will be the second material property. So, essentially your material property is tau y to the power 2/3. In order to minimize the mass against shear, you have to minimize this, and that means you have to maximize this capital M, which is tau y to the power minus 2/3 over rho. So, tau y to the power now we cannot write it as minus 2/3, this will become 2/3. So, it is tau y to the power 2/3 over rho. This is what you have to maximize if you have to sort of get a better material property. Okay. So, we got these two indices here with us, that is, one is this one and another is that square root of and another is that other property, that is square root of g over rho. Okay. So, we will keep that in our mind. Okay. Now, with that, let us go further and let us take up another type of a case. Okay. The second case study now we want to do is design a lightweight aircraft wing shear wave. Okay. As I told you that the shear wave is nothing but the wing has two parts, right, the top plate and the bottom plate, right, whatever is the top and the bottom, that is the aircraft wing, and shear waves are these waves that are joining them. Okay. So, this shear wave, we have to assume uniform shear, otherwise there will be some correction factor. The objective is minimize the mass of these shear waves while carrying a prescribed transverse shear load. Okay. So, carry the shear force that is given to you, minimize the mass m, fixed length L, fixed shear V, and design may be stiffness limited or strength limited. So, that is what we are going to see now. Okay, so, there are two cases just like the shaft. The first case is shear stiffness limited. Okay. So, in this case the shear deflection delta is VL over AG. Okay. So, that if you simply do this consider this block, okay, consider a simple block which is undergoing a shear, right, something like this, okay, and this is of length L, okay, and this change is delta, right, and then the shear stress equals to this G times the shear strain. If you do, you are going to get this relationship. Okay. So, that is the shear deflection, and in this case area is the free variable, okay, because it is not a shaft, it is just the area. So, that area will now become VL over G delta, okay, because your shear deflection is limited. Now, mass is rho AL. So, that means I can write this as rho times VL over G delta times L. That means this will become rho, okay, by G times L square over delta times V. Okay. So, this part is our functional part, and this is, so F, this is our geometry, and this becomes our material property index. So, this is Mi. Okay. So, in order to reduce the mass m, I have to reduce this rho by G. Now, we have defined the inverse of it as the m, capital M, that means I have to increase this G by rho. So, that is our shear stiffness limited design for this aircraft, simple case of a aircraft wave shear. Now, if it is shear strength limited, then of course, I have to consider tau y, and then of course, the area required will be simply V over tau y, and then that comes into the mass, and then the same way you get rho over tau y, and that means the material property index will be tau y over rho. Okay. So, that is the case for this type of a situation. Now, let us go and put all the material properties that we know. I have also added some extra materials now, like pick also I have added here, and brush also I have added here. Okay. So, if you put all the material properties, also you will note that the aluminum alloy I have added here is 7075, that is generally used for aircraft. Okay. And steel 4340 is known for its high shear strength. So, if we use each one of them from the G rho characteristics part, again you will see CFRP is number 1, number 2 is steel, then titanium. So, now the picture is changing, steel is now number 2 actually. Okay. So, whenever it is you are changing from shaft to the vertical wave, immediately steel comes into picture, and then titanium. Magnesium alloy comes below that, then aluminum alloy. Brass comes after it, but brass we hardly use. Then GFRP becomes another interesting one, and wood is there, okay, PIC is there, chalk is just for your sort of an idea that where the ceramic materials are placed. I want to tell you two interesting observations. One is that GFRP and wood, okay, wood has 1.54, it is not so much out, and hence most of the model aircrafts they actually use wood, okay, because that gives you a good sort of a shear for a stiffness limited design, and then shear strength and for a shear stiffness for a stiffness limited design, and then GFRP also. Okay, GFRP is in fact quite comparable to even brass, for example. Okay, so lesser than aluminum alloy, but it is quite good. So these two are something that are regularly used for such applications, but of course carbon fiber reinforced plastic remains the best in this category, no doubt in it. Now, if I go for the strength, are we going to retain the same scenario? See, CFRP has now become number 3. Okay. Titanium is number 1 now. Okay. Though titanium we will not use because it is difficult to actually sort of shape the titanium. Okay. So, manufacturing with titanium is having much more expensive. So, otherwise titanium is good. Next to it is aluminum alloy. In fact, you will be that 7075 is used in a very big way in one of the Indian transport aircraft, okay, which is based on aluminum alloy. Okay. So, the wings and all these cases they use a lot of aluminum alloy. So, aluminum is the next best to titanium, and as I told you, titanium has a machining problem, but aluminum does not have. So, it is good. Then the CFRP comes, okay, and then the steel, and then magnesium, PIC, GFRP, brass, wood, etc. So, you see, depending on what you want to sort of limit your design on, whether it is stiffness or strength, the material varies. Okay. So, the points to note is that different objectives lead to different optimal materials. CFRP dominates in specific shear stiffness, but titanium and aluminum alloy excel in specific shear strength. Okay. Specific means something which is divided by the density. Steel remains a practical engineering choice. Rubber is ideal for damping, so for coupler it is good, and Ashby index provides the fast screening very well. Final selection requires many additional constraints, which later on when we will do product by product case study, I will tell you what are the additional constraints that come up. Now, if I expand this for all the possible torsion and shear conditions, okay, automotive drive shaft, root of G by rho, racing drive shaft, again root of G by rho, but in this case it is CFRP because it is a racing car, okay, and the other case it is steel, CFRP or aluminum depending on the type of use. Transmission shaft, steel is a good one because the strength is important there, and then the tau y over 2/3 by rho, the steel takes a good position. If you go for helicopter tail rotor shaft, then you have to use CFRP or titanium. Okay, though titanium is difficult to actually machine, but you will have no other way. Torsion springs, again spring steel. Shear pins like those cases of bolts and rivets I told you, steel or brass. Aircraft wing shear wave, CFRP or aluminum I just now discussed. Bolted joint, alloy steel, riveted joint is aluminum. Okay. So, that is generally the practical applications, and you see all of them follows from the table that I have described just now to you. Now, I come to the second and the last important topic in this part, that is the Ashby triangle. Okay. So, this was actually introduced by Professor Michael Ashby, and what he introduced is that when I select a material, we will not only select it from material property index M, but also, so M is one part of it, but also the shape and also the process. All three of them will play important role. Okay? So, intrinsic properties of materials that are already there, but in the shape it is the geometry that may govern the load carrying capacity. Okay? Example is like I-beam, hollow tube, sandwich, honeycomb. These are all geometry dependent cases, and the process, like whether you are going to take casting, forging, extrusion, injection molding, additive manufacturing, that is also important. So, when I choose a material, then actually my choice of geometry also is to be coming with it, and then next to that is what manufacturing process I am going to utilize. And depending on all these three things together, because they always interact with each other. So, the selection process is continuously iterative in nature, that we have to keep in our mind. Let me explain that point to you. Okay? For example, aircraft wing. Okay? CFRP if you take, then you can have a box beam configuration, and automatically that is the geometry, and automatically the manufacturing process will be autoclave process. Okay? So, if you consider CFRP as your decision, then the geometry and the manufacturing process gets fixed along with, and remember autoclave is a very expensive process. Okay? Let us say bicycle frame. Let us say you are telling that I am going to go for aluminum. Okay? Then it is hydroforming that becomes important, and geometry is of course a shaft of it, and that would be a hollow shaft. Then the beverage can, if it is aluminum alloy, usually the manufacturing process will be deep drawing. Wind turbine blade may be composite plus resin infusion. So, our design process now, earlier I said that it is function, constraint, objective, free variable choice, Ashby index. Now, I am going to add one additional point following the Ashby triangle, that is optimize material, shape and process simultaneously, okay, to get the best solution. A specific example I want to show you is in the context of today's lecture, that is for shaft design. Let us say a transmission of torque is the function, we know, constraints also we know, strength, stiffness, length, safety, cost, etc. Free variable from the material point of view, it was the diameter of the shaft, but then the shape and process. Okay? Now, for strength limited design, suppose if the diameter is the free variable, the material performance index is tau y over 2/3 by rho. However, if the shape is also a free variable, then it is no longer a solid shaft. Okay? I can go for things like hollow shaft, right. I have not shown you, in fact that will be an exercise that we will do at a later time, that what will be the material property index if I consider only a hollow shaft. Okay? Then it will no longer be tau y 2/3 by rho, it is going to get changed. Okay? And if it is a thick shaft and a thin wall shaft, the result is going to get even further different. Now, you see, I choose any one of these geometry, the next will be what manufacturing process. Okay? If it is a simple solid shaft, machining would have been all right, but if it is a hollow shaft, well, for some material you can use, like aluminum, you can use extrusion, okay? But for composites you have to use filament, and for some other material you have no other way to go, particularly for thin walled type of applications, you have no other way to go but to go for additive manufacturing. So, you see, all the three things comes together, that is the point we have to keep in our mind. Okay? So, detailed Ashby triangle, how it influences the design decision. For example, if it is yield strength that comes from the material side to be your dominating point, then you go for hollow shaft, and the process you should adapt is extrusion. If it is shear modulus, go for thin wall tube, and the process is the filament winding. If it is density, go for lattice shaft, then additive manufacturing is your only answer. You will see in metastructures we actually do that. If it is fatigue strength, variable thickness, then forging can be an option. If it is corrosion resistance, ripped shaft, heat treatment could be an option. So thus the Ashby triangles works as the final judgment beyond the material property index M. That is the point I wanted to tell you. Okay. So this is where let us finish today's lecture. Thank you.